So after the finite element analysis of these models, we can represent the results in this form like load versus the force versus displacement of the fairing. So the model 1 is blue color, which has minimum area under this isolatic curve, and model 3 has highest. So that each and every model are the statistics graph of every model is open, and that load displacement data is also recorded. So these are the results. You can see that the first one represents the thickness of rubber layer, thickness of steel layer, and lead core diameter and the strength of lead. So results of this parametric study are here. So this graph shows change in effective stiffness with rubber and lead core diameter. The changes in rubber and lead core diameter. So this for 5 mm thickness of rubber layer and 200 mm diameter of lead core, that effective lateral stiffness is 3100 kilonewton per millimeter. So like this we can read this graph. So this graph represents changes in effective lateral stiffness with steel and lead core diameter. The previous one showed with rubber layer thickness and lead core diameter. This one showing with steel layer thickness and rubber lead core diameter. So for 3 mm thick steel layer, the effective stiffness will be more, like around 3500 to 3700. Though this graph shows that damping ratio or equivalent viscous damping ratio with of that different lead rubber bearings with variation in steel and lead core diameter. A steel plate thickness of 2 mm and lead core diameter of 200 mm has highest viscous damping ratio, so 45 to 48%. That equivalent viscous damping ratio is nothing but the damping ratio that are it represents how much energy is dissipated by the lead rubber bearing, like how much of input energy is lost. So for 20 mm rubber layer thickness and 200 mm lead core diameter, that viscous damping ratio will be around 50 to 52. This one shows equivalent damping ratio with the yield stress and lead core diameter. So this one showing the vertical stiffness of the lead rubber bearing at rest. Like it is when lead rubber bearing is not subjected to any lateral deformation, what will be the vertical stiffness with variation of rubber and lead core diameter, rubber layer thickness and lead core diameter. So this graph represent that same vertical stiffness when that lead rubber bearing is subjected to 150 mm lateral displacement. What will be the vertical stiffness with variation of rubber layer thickness and lead core diameter? As you can see, as the rubber layer thickness increases, that lateral stiffness or vertical stiffness of that rubber bearing will reduce greatly while bearing is subjected to lateral displacement.